Welcome back. In the last episode, we got mass points falling under gravity with verlet integration, but a single falling dot isn't very interesting, of course. So what makes glove simulation work is the connections between points, and those connections are called constraints. This episode, we're building a constraint class, adding two new helper methods to Vector2, and implementing mouse dragging so you can actually grab points and move them around. By the end, we will have 3 points connected into a triangle that we can interact with. Let's take a look at the constraint.js class. Note that this constraint is also called a distance constraint. So constraint is actually just an abstraction. You can have, or there are multiple constraints, like for example, volume constraints and density constraints in position-based fluids. So for the glove simulation, I just call it constraints. You can also call it distance constraint, for example. But anyways, a constraint connects, in our case, two mass points. When we create it, we measure the distance between the 2 points and store that as a rest length. This is the distance the constraint wants to maintain. The strength parameter controls how aggressively it corrects. 1 means full correction, lower values makes it way more soft. And let's now take a look at the update method, the constraint solving basically. Here is where the magic actually happens. Every frame, the constraint checks how far apart its 2 points actually are compared to the rest length. If they drifted apart or they've been pushed together, it calculates a correction. The correction is split 50-50 between the 2 points. Each one moves half the distance. And point A gets pushed away, point B gets pulled in, or vice versa. The strength controls how much the correction was actually applied. A strength of 1 means correct fully, and low values let the constraint be a bit springy or softer. If you correct it with a strength of 1, there's a chance that the simulation gets unstable or it overshoots. So usually a lower value of 1 is the best. And this is position based. We are directly moving points, not applying forces. That's typical for verlet based constraint solvers, and it's part of why the system is really, really stable. There are, of course, glove simulations where just normal forces are used, but those are normally less stable than position-based glove simulations. And then we have the draw method. This is really, really straightforward. We just draw a line between the 2 points with the 2 positions of the mass points with the color of black and a line thickness of 10. So let's take a look at the mass point class first. We have a new method there, and this is called isInside. It is pretty straightforward. This checks if a given position, like a mouse position for example, is within the point's radius. So we use it to figure out which point the user clicked on, for example, and like you can take your mouse and then we know, this mouse position is inside that point, so it's easy for us to drag a point around and so on. And then we have a method for a new method for the vector class. This is a copy method. Copy makes a copy of the vector. We need this because JavaScript passes objects by reference. When we drag a point around, we set its position to a mouse position, but if we just do point position equals mass position, a mouse position, both variables point to the same object and weird things will happen. Copy gives us a clean independent copy, a deep copy. This happened to me in the past pretty often, so I learned my lesson and just do copies. Okay, and then we can also implement the mouse dragging now. At the playground.js file, we drag the mouse position, which point is currently selected, and which point is currently selected. In the update, if we have a selected point, we snap both its position and alt position to the mouse position. Setting alt position 2 is important. If you only set position, then on the next frame, verlet integration would see a huge difference between position and alt position, and the point would launch off in random directions when you release it. By setting both, the point has zero velocity while you're holding it. Then we have some additional methods. On mouse down, we ask the simulation if there's a mass point under the cursor. If there is, we grab it. On mouse up, we release it. The point keeps whatever velocity it had from the mouse movement, so you can throw things around. Okay, now let's head over to Simulation.js and create our little triangle demo. We set up 3 mass points in a triangle formation and connect them with 3 constraints. Gravity pulls them all down at the same rate. The constraints keep them at fixed distances from each other. Then we have a new method, get mass point at position. This loops through all points and checks if the given position is inside any of them. The update loop first updates all points, so gravity plus verlet, then solves all constraints. Order matters here, physics first, then constraint corrections. The draw method now renders both points and constraints, and this is all for the Simulation.js. Now you can actually run the simulation. Also, a short recap. We built constraint class that enforces distances between 2 mass points using position-based correction. We added isInside to mass points for hit detection and copy to vector2 for safe copying. We wired up mouse interaction in Playground so you can click on points, drag them around and let go. The triangle demo is actually a tiny softbody. So grab one corner, the other one will follow because of the constraints. This is the same principle that will make the glove work basically. So just way more points and way more constraints, and it gets way more interesting. So what's coming next? Next episode, we are going to look at the verlet integration more closely. The standard version we have now assumes a constant time stepping, but in practice, request animation frame doesn't give us perfectly even frames, so we will implement a time-corrected or improved version that handles variable time steps properly. We will also add a wall collision on the x-axis, and so we can see that the particles are not just falling through the canvas, they actually bounce off something. And that's all for this episode. Thank you very much for watching, and see you in the next one.